Okay, so we've invested some time now in thinking about carbonyl carbons, nucleophiles, and then in the last section we considered a nucleophile as water, right? Boom. And something similar to water. I'm trying to do these lone pairs of electrons nicely, right? And we got good at that. That's something we can do, right? So oftentimes directing these mechanisms, we have memorized in the back of our mind what we know what we're going toward, right? So that really helps us with our mechanisms. Now what we're going to do is something even more similar. Well, no, it's not really more similar, but I guess the next story, right? What you might expect. It's a similar thing though, right? Can you see how this is going to be the same? Because I have a lone pair of electrons on an electronegative element, a lone pair of electrons on an electronegative element, a lone pair of electrons on an electronegative element. Can you see where I'm going with this? And then look it. Can you guess where I'm going now? Watch. Right? Another version, but these are all the same thing. Okay, not the same thing. I admit. Little variation. But it's like the difference, you know, if you knew how to count 21, 22, 23, 24, 31, 32, 33, 34, 41, 42, 40, right? You just, you see, oh, it's the same thing. All right. Now, here's some questions we're going to probe in the next few slides. If you want an amine, where's my pen here? If you want an amine to attack a carbonyl carbon, will a catalyst be necessary? I think that's a hard question. Will a catalyst be necessary? Is that good enough to come in without a catalyst? And the answer is going to be, is the carbon open enough? Is the carbon positive enough? That's the electrophile. Is the nitrogen negative enough? Right? That's what dictates that. All right. Now, if we have a catalyst, will a proton, where am I here? Will a proton or hydroxide be most likely to work? And why? Why would that be the case? So let's think about that. This we're definitely going to answer, and I wish I could require you to right now stop the video and think about that and draw out the possibilities. You would learn it better. All right, I'm going to suppose that I can't compel you to do that. I'm going to move on. What will the product most likely look like? So what are we expecting? When we brought water in and alcohols in, I know this is just getting busy, isn't it? Waters and alcohols, when we brought those in, what did we get? We got acetals, remember that? And hemiacetals? All right. Now, when you, what's going to happen if you bring nitrogens in? Oh, that's what we're asking about. What's the product most likely going to look like? Now, keep in mind that entropy disfavors processes in which two molecules combine to form one. Okay? So there is something pulling against it, and that is entropy. Analyze the complete mechanism. Next page. Let's go there now. We're going to see mechanism 20.6 is going to look like 20.7 in some variations. All right, so these, let's really get this mechanism, and you're going to see it looks like 20.5 and 20.4 also. All right, so we're just what you expected. You have an amine. In this case, it's a primary amine, right? A primary amine, and it's a nucleophile, so it comes in and attacks the carbonyl carbon. Boom. Right now, at this point, I'm thinking you have 0 charges here, 0 charges, and then you've got 2 formal charges. Look at that. So you would, if you were expecting this to really go more in that direction, that would be understandable. Okay, but you do, if you've got some amount of acid around, you can take care of one of those formal charges, right? So this becomes neutral, okay? And then this conjugate base that you formed here comes and takes that proton and goes back to being an acid. Okay, and here's the acid now. Then we get another proton transfer. Proton transfer, let's look at this. This is a proton transfer. This is a proton transfer. This is a proton transfer. This is not. This is not a proton transfer. Right? Now, we have water as a leaving group because we transferred another proton on there. This is exactly what we had in the previous mechanism when we were making acetals. Go back and look at it. Please consider pausing the video now and going back and looking at and finding that very step in mechanism. I don't even know what mechanism. I'm going to look it up right now though. It's mechanism 20. Looking at it. Mechanism 20.3. This is identical to 20.1. Now, for acetal formation, yep, go look at mechanism 20.5. Where am I? Where's my pen here? Look for this in mechanism 20.5. It's on page 941. Page 941. Find this very step in it and you'll see it's the same thing. Okay? So, now that is water leaving, right? That's what we have going on. Water leaving. Now that we have that, you see that we have another proton transfer, right? So 5 or 6 of these, no, 4 of them are proton transfers. 4 proton transfers. So really what this whole point of proton transfer is just making something stable so it can leave, right? And then we get this amine. We get the nitrogen on there, all right? So I would drive this mechanism. We're going to do the same thing with 20.7. I would drive this by memorizing. I have that. It's eventually going to go to that. If you have this memorized, then you know you've got to get rid of the oxygen, right? I got to get rid of the oxygen. I got to bring in the amine. You know there's a lone pair on here, and you know the carbonyl carbon's where it's at, right? So you bring that in. This is the big deal. That, and eventually we got to make this a leaving group. It's got to go, and a good leaving group is water, right? Is this water? No, it's not. It's got too many bonds to carbon and too few bonds to hydrogen, right? So consequently, we got to do a bunch of proton transfers, and that's what that's all about. All right, let's move on. I understand that's too fast to be really good at it, but we're going to see it, the same mechanism over and over again. If you have the spirit for it, you should pause the video now, get a blank sheet of paper, and memorize this mechanism. And just think about it like this. Here's your reaction. Whoops, whoa. Sorry. Here's your reaction. And memorize this mechanism. And you will be so set for the rest of this conversation. All right. Now, the mechanism requires an acid catalyst. Why is that? Well, something you might not have necessarily been able to to guess, and that is that this crud, just a second here. It's just ugly. I gotta get rid of this. Eraser. Okay. This is not a good enough electrophile. This is partial positive. This one is partial positive. Can you see it's a lot bigger, right? Much better electrophile. Much better electrophile. So, and you know that. Now, I think on the next slide I'm going to ask you why does the rate of the reaction fall off down here? That's too acidic here, right? And here it's too basic. Why? Why do we need the proton here? And if we get too many protons, we got a problem. This really makes sense when you see it. Okay, practice with skill builder 20.3. All right, this is a question I asked in a previous slide. Why does the reaction slow down at pH below 4? It slows here, and it slows down here. And it turns out this is just the right one, okay? What makes something too basic? Go back and look at this mechanism, and what makes the mechanism too acidic? I'm not going to answer that for you. You really need to see it. And then after you've wrestled with it, if you're stuck on it, please let me know and I'll tell you. It'll make so much more sense if you wrestle with it first. Okay, now let's talk about secondary amines. As I promised, we're going to first of all, the last step of the mechanism 20.6, you get a proton transfer right here. But if you do a secondary amine, you won't have a proton there to take off. You see that? And so if you take this proton off, you retain your double bond there, and this is called an imine. But if there's no proton there to take off, well then your base, which is coming in, the last base that you have coming in to take this off, I mean, this is going to be the best one to take off, right? And can you see it goes there? So can you see a double bond there, N or ene, right? So it's an amine, all right? So mechanism 20.7 is identical to 20.6. Except this last proton transfer step. Now I encourage you to pause the video now and to take the mechanism which you've just recently memorized and do it out again, but this time do it with a secondary amine. All right, this is a tedious process, but you've got your book, and mechanism 20.7 is on page, where am I here? Mechanism 20.7 is on page 952. Please consider not even looking at it, taking 20.6, which is on page 948, and changing it to a secondary amine, making the necessary changes. Does that make sense? Go to page 948. Go to page 948. And instead of using a primary amine, use a secondary amine. Okay? And figure out the difference. Where this is where it is, all right? I'm not sure, I don't feel like I made that description very clear, but do this. Okay? All right, good luck. Let me know what you think. Okay, now, the last thing we're going to learn in section 20.6 is a Wolff-Kishner reduction. And we're going to memorize this reaction. Here's a reaction we're going to memorize. Okay. You know what? We're going to memorize the whole thing. Sorry. Okay, so it's 2 steps. 1 step and 2 steps. You got to keep them separate, of course, because this is acid catalyzed. And this is base, right? So you have to keep them separate. But we now have a way to take a carbonyl carbon and completely get rid of the functionality. All right? And this is called Wolff-Kishner reduction. Hydrazine attacks the carbonyl carbon, so this is going to look just like mechanism 20.6 to form the hydrazone, which is structurally similar to an imine. So you can see that, you saw that before, right? This is called a hydrazone, but it's just because it's got this other thing on it. It's like an imine, okay? And the second part of the mechanism right here is mechanism 20.8. So we're going to do this right here. Next slide. Okay, so a bunch of proton transfers. Look at this. Bunch of proton transfers, proton transfer, proton transfer, all for the purpose of making a good leaving group. Right? What's the leaving group here? Nitrogen gas. Okay? All right. So we get a base that comes in and takes this proton. And that proton, or rather these electrons go here and then down to here. So it wouldn't hurt you, I think, just to do all that. Oops, just 1 second here. In one step, right? See how they did that? They go down to there. But if they go there, I don't think this is concerted, actually, all right? So, no, you really can't do that. If it's not concerted, I'm sorry. I beg your pardon. Misstep there. So these go here, and you get a negative charge on a nitrogen, okay? Now, when that happens, you have a resonance structure. This negative charge is shared with the carbon, right? And this, you know that carbons do not like to have a negative charge. So it sees this water molecule, which was made over here. I'm sorry I keep doing that with my hand. Get this hydroxide here, which turns into a water molecule, right? And so the carbanion takes that proton, right, and leaves you with this structure. And we just do the same thing again. Exactly the same thing the second time. Okay, so the hydroxide. So I'm going to say, look, this step right here, I'm going to call it X. Looks just like this. X, right? It's a hydroxide coming, taking a proton off. Okay? This Y looks just like this. Y. You see it? And this step, Z, looks just like this. Z. Right? So again, I would say that you know we're going to take A plus B and produce C. You know this is the reaction. And this is what you're given. You're given those guys, and you know you've got to go to C. So you think to yourself, how can I get to C? So in this case, the product is nitrogen gas. Right? We're going to make nitrogen gas out of this. So in order to do that, we've got to get rid of these hydrogens and make extra bonds here. And get rid of those bonds. Right? And you also know that we're getting rid of these bonds and we're making, right? So if you think about it like that, you know where you're going. I remember in 1976, I was sitting in the back seat of our car, and I was watching my dad drive me to school, and I was thinking, this guy is a total genius. How could you possibly remember to turn at all these different places? Because he just kept making these bizarre turns, and I was like, wow, it's amazing to me that my dad is so smart. Was my dad that smart? Or he's still living, thank God. So is he that smart? Well, he's a pretty smart guy, but if you think about it, that's not really that much evidence of utter genius, is it? The thing with my dad was he knew where we were going, and he knew in general what it was going to take to get there. And you do that every day when you drive to school. You know where you're going. It's not that you memorize a bunch of turns. It's that you know where you're going. And you know in general what it's going to take to get there. And that's what we're doing here. Same thing with these mechanisms. All right, I think I have one more slide here to go. Yeah, this is the last one for this presentation. So note the many similarities between acid-catalyzed mechanisms which we have discussed. Carbonyl is protonated first. This is very cool. The carbonyl is protonated first because it's acid-catalyzed, right? The carbonyl is protonated first, which makes the carbonyl more electrophilic. And it avoids a negative formal charge on the intermediate. More so, it avoids high energy intermediate that has two formal charges. Right? You don't want that. You don't want a high energy intermediate with two formal charges. The acid protonates the leaving group, which we've emphasized a couple times, so that it is stable and neutral upon leaving. And the last step of the mechanism involves a proton transfer, forming a neutral product. Overall, under acidic conditions, reaction species could be either neutral or having a +1 formal charge. This is a common mistake. Sometimes I'll look at someone's mechanism and I'll see a negative somewhere, and under acidic conditions, you never have negatives. Does that make sense? I mean, unless it's like chloride in HCl, or I should not have said negative. I should not have said never. But you won't see a negative charge on an oxygen. I wish I could just walk that back. Okay, I'm gonna cut the video off there.